C's, and that's good. And the B's are back to life. So once the Turing machine puts the B's back to life, it hits this cross-out C, then it can run back till it hits the first cross-out A. She's an uncrossed out C. Now it goes back looking for a live B. Doesn't see a live B, but does see a live A, and so it goes back, turns the B's back to life. Hits the crossed out C, so it doesn't, it's at the end of the B's, comes back here, hits the crossed out A, looks right, there's a live A, so does that. Then here, and here, okay, goes back, the B's all crossed out, goes back looking for a live A, doesn't find one, okay? It doesn't find a live A, it's only a crossed out A, okay? At this point, what it knows is that you've used up all the A's, okay, so you've gone through this whole cross-out business the number of times equal to the number of A's. And each time you did that, you crossed out a number of C's equal to the number of B's here, okay? So at that point, it definitely knows that the number of C's crossed out is the number of A's times the number of B's. That's the logic of what it did, okay? And by the way, suppose in this whole business you didn't have enough C's, okay? Well, you've got to go back to the control too. While it's zigzagging back to the B's and the C's, if it ever runs looking for a live C, a non-crossed out C, it hits an empty space, and then it goes into a reject state, okay? But now, if we've actually gone through, we've crossed out all the A's, so we know that the number of C's we've crossed out is equal to the number of A's times the number of B's. So what should it do now? What? Yeah, it needs to go all the way to the right here and make sure that there aren't more C's. So it goes to the right looking for a C or looking for an empty space. And if it finds a live C, but if it doesn't find a live C, it finds a space, then it accepts. Okay? So I'm describing this at a high level, and I've shown you some little pieces of how the finite control would work. And all of you should be able to take that description, what I did, and it's basically what the book does too, and actually turn that into transition written out transition rules, transition functions, which describe exactly what I was doing. And when you do that, or if you write it as a diagram, you want to group together certain transition rules and say, what these transition rules are doing are the zigzagging, between crossing out a B, looking for the next C to cross out, crossing it out, and go back. So you can describe your Turing machine not just as, here are a whole bunch of rules, now, go try to read them and verify yourself, but here are the rules that do this logical operation related to the high-level description of what the Turing machine is doing. And here are the rules that implement the next kind of logical operation, and here are the rules that move the Turing machine from this kind of logical operation to that kind of logical operation, and so on. And here's the rule that checks to see if there are any additional C's, and so on. Does anybody feel like you could actually do that? Does anybody feel like you want to do that? Good. Yeah, it's something you should do once or twice. Just like programming or assembly language, you should do a couple of times to get a feel for it, and then never do it again. Have a good intuition of what you can do. Okay, so I don't know whether the book specifically asks you to do that in the homework, but I'll put that on the next homework, which should be available tonight or early tomorrow. All right, so it's a question of timing, because we have a midterm next week. This is Thursday, next Thursday. So I won't have the homework due on Thursday, it'll probably be due the Tuesday after that. But you definitely don't want to stop working now because we have a midterm in a week. So this question will be on it to actually write up full transition rules, either as literal rules or in a diagram, and make sure that you can actually program this. Okay, so the book has another, after that, there's another example of coding a transition. Yeah.
So just your starting for that. Can you quickly go over using also be able to do this term?
I think the question is what's the term to cover. And certainly anything about IC machines and PDAs, the question is how much of Turing machines. I would say I would have at least one question on programming a Turing machine. Some language, and say, try to describe either as a diagram or a transition rules or a high-level algorithm, but in a way it's low enough, it's detailed enough that it's clear that can be translated into a real Turing machine. So one question at least on programming a Turing machine. And so that really takes us to today's lecture, essentially. But to right now, what we've been doing is looking at the rules of the Turing machine, the mechanics of the Turing machine. We've done a couple of actual examples of programming a Turing machine. And later what we're going to do today is a theorem and a proof, and so that, I would say, is sort of the dividing line between what would be on the midterm and what wouldn't. Okay, that doesn't mean you shouldn't pay attention to the rest of the lecture. In fact, I think today's lecture is the hardest. What's coming is one of the hardest parts of the whole course, so you want to pay attention to it. And okay, so that answers your question. I'll make it up. And some people would ask for a sample midterm. There's no way I can write one in time. I usually struggle to get the real one done in time. I can find old ones, and they may correspond to exactly where we are in the course, and they may not. I'll try to find one of those. What do you like review? A review? Well, it really is up to Sean whether you want to talk about current homeworks or the questions that you have, or whether you want to do a review. I don't know. I think the question is I'm not going to do a review. Yeah. But whether you're going to use your discussion time to do that is really, I think, up to how pressing people feel about the next homework. Okay. So, all right. So anyway, the book has another example that goes into some detail before it moves on to the next topic, which is variance of Turing machines. Anyway, variance of Turing machines. Lots of different variants of Turing machines. For example, first one, the book actually doesn't discuss very many, but it has some of the homework. There are other books that I have that have 8 or 9 different variations and things that you can imagine. A Turing machine with a stack, or a Turing machine with multiple heads, or a Turing machine with infinite tape. That's the tapes that we've always been looking at are finite at one end, there's a starting point, and then we go infinitely in one direction. But what if you could go infinitely in 2 directions? You could write that way as a starting point where the input is, but you're permitted to write things to the left. Does that help? And all of those things, when I say does it help, when we formalize that is whether or not the set of languages that are recognized by this kind of Turing machine is the same, or is it different than the set of languages that are recognized by a Turing machine that has some additional gizmo? Okay, or is the set of languages that are decided by this class of Turing machines, is that equal or different than the set of languages that are decided by a Turing machine that has some additional contraption? Okay, and two types of Turing machines are called equivalent, or 2 Turing machines are equivalent if they recognize the same language, or if one is a decider, then they both decide the same language. Okay, and so we're going to look at the variant which has multiple tapes. So you have a finite control as before, and you have a tape, and this might be where the input is. But you also have another tape that you can use, and maybe you have many. Maybe you have K-tapes. Okay. K is some finite number. I mean, this is the Turing machine is well described. It has some finite specific number of tapes, and in particular Turing machine does. It doesn't have an infinite number of tapes. But in conceptualizing this class of Turing machines, we don't put down to what K is. So there's some Turing machines that have 2 tapes, some that have 3, some that have 16, some that have 1,000. But it's always a specific number. And we represent that specific number as a variable K, or K tapes. Okay? And then what do the transition rules look like? Well, transition rules, again, you're going to be what state is the Turing machine in. Okay? What symbol is it reading on tape 1? And what symbol is it reading on tape 2? And what symbol is it reading on tape 3 all the way to tape K? Okay. So it's got multiple heads, and therefore it has multiple sources of information. And then based on all of those, it's what state it's in, and what state it wants to move to, and then what it's going to do on tape 1. Is it going to go left on tape 1 or go right on tape 1? Cross what's going to right on tape 2? Is it going to go left on tape 2 or right on tape 2, etc.? So a very natural generalization is just instead of deciding what to do on one tape, it decides what to do on all the different K tapes. And it's going to decide what to do based on what state it's in. It's still only in one state. And what it's reading from all of the different K tapes. Okay? So is this equivalent? The question is the set of K-tape Turing machines equivalent instead of single tape Turing machines. That is, if you have, i.e., if there is a language recognized or decided by a K-tape Turing machine, is the language also recognized or decided, depending on what kind of Turing machine it is, decided by a single tape. Okay, that's what equivalence means. Although actually, from a purely formal standpoint, this is only half of what equivalence should mean. What's the other half? Yeah, you're going to have to say trivial, we don't even put it up, but formally it is, the other side of this question, is there a language, if there's a language that's recognized by a single tape Turing machine, is the language also recognized by a multi-tape Turing machine? Well, yes, because the single tape is also a multi-tape. I mean, it's with K is equal to 1, so that's fine. The class, anything that can be recognized by a one tape, any language that can be recognized by a one-tape Turing machine can certainly be recognized by a two-tape Turing machine. Okay, what does that two-tape Turing machine do? It just ignores the second tape. It runs exactly like what a one-tape Turing machine does, and just ignores the second tape. But if you had a two-tape Turing machine and you were literally writing out the transition function for it, you would always have to include in the transition function that no matter what is on the second tape, well, the second tape will be empty, so you don't do anything with it. You just do nothing with it. Okay. But anyway, certainly anything that a single tape Turing machine can do, a two-tape Turing machine or a three-tape Turing machine or whatever can do. Okay. But this direction is the interesting one. So what do people think? Is two heads actually better than one? Well, not in this context. No, two heads are not better than one. Two tapes are not better than one. You can simulate. So the question is associated with equivalence, and the answer to the question is yes. Okay. And the proof of that is that we can simulate any computation of a K-tape Turing machine with a one-tape Turing machine. So let's get into the first, what's a really important concept in Turing machines and study of languages is the idea of simulation. All right. So what do we have to do in order to prove that we can simulate any computation of a K-tape Turing machine with a one-tape Turing machine? We have to, what we, the provers have to do, describe in some generality that if you ever had a multi-tape Turing machine, and you have its transition functions as multi-tape, let's just say, for the picture, sake of the picture, it's two-tape Turing machine. So, given a description, given a complete specification of a two-tape Turing machine, we want to come out with a specification of a one-tape Turing machine, where we can prove, or this is usually pretty obvious, that any computation that's done on this two-tape Turing machine will have an equivalent computation on the one-tape Turing machine. And so this computation will end up in an accept state, if only if this computation ends up in an accept state. We'll be able to go both directions, if and only if. Okay, so what's the idea of this simulation? The idea is that the one tape is infinite. So there's plenty of room. There's no, we're never going to run out of space. We can always grab more space if we need it. All right? So the one tape, the single tape, is going to basically encode, well, let's just for the sake of clarity, first just talk about a two-tape Turing machine. So I want the single tape to be able to always write down on its one tape what the contents of the two tapes are in any kind of computation that the two-tape Turing machine is doing. Okay, so here's the two-tape Turing machine. Here's tape 1, and here's tape 2. Okay, and tape 1, that's on one tape is where the input comes, and the other tape starts empty. Then as the computation goes on, tape 1 can have something other than the input because the Turing machine can write onto it, and this tape can have things on it too because the Turing machine can write onto it. But at any given point, there is something that's written on this tape. I don't know what it is, A, B, B, A, C, whatever. But it's a finite amount. It's not, even though the tape is unbounded, it's infinite. What's written on the tape at any given moment is some actual finite number of symbols. So it ultimately hits a blank. And the same thing over here, B, C, A, B, C, whatever. Finally some blank. All right, so, and then as the Turing machine progresses, it's in some particular state. It still only has a single state that it's in. Okay, multiple tapes, but it's the same kind of finite control as before. So what do we want the simulating one-tape machine to do is to have on its tape the contents of tape 1, A, B, B, A, C, down to there, then some kind of mark which says, that now I'm going to be writing the contents of tape 2, B, C, A, B, C, down to there. So I have to tell you how we're going to update this because it looks a little compressed. What happens when you do in tape 1? What happens when you write something into a space? This is only a single space here. All right. But this isn't infinite. This isn't, the first part can't go forever because then there's no room for the second tape. So we're going to a single space here. And what happens if in this computation we write something into that space? Down here we want to write that in that space and put another space there. Okay. But you can't insert it into a tape. A tape is a purely sequential thing. Well, what can you do? I'm scratching your head or answering.
I think you just added the half a second.
Okay. Anybody have a suggestion?
I do copy this.
Yeah, you can move it seamless, but you can move everything down. Okay? You can, if you're, remember, this has a finite control in here, and it's going to write something, it wants to write something into the space, that's fine, it writes it there, but now it wants to put another space there, and there's no room for that. You can enter a part of its finite control where it moves everything to the right, one space to the right. Okay? How does the Turing machine do that? It runs to its, the end, okay? Now, this one's only 2 tapes, so it runs to that blank, okay? And then it backs up by 1, let's see, moves that over, yeah, well, okay, yeah, it finds the blank, moves over by 1, writes that there, okay, and puts a blank there. Then goes to the reference piece of character, writes that there, puts a blank there, and so on. Okay, so it's tedious, but you can certainly write the finite state rules. It's tedious for the machine. For you, it's not that difficult to write the rules that would move everything on tape one space to the right. So think of that as a subroutine or procedure or whatever. A small computation, small part of the Turing machine program that with the small task of moving everything one place to the right, just written on a tape. And you should see that that's a very simple thing the Turing machine can do. So if it ever needs more space on some portion of this tape, you can move everything to the right by 1 space. Right. What else does the Turing machine need to know in order to represent the kind of computation that's happening in this Turing machine? So we can write the contents of both of these tapes on a single tape, but we also need to know where the read heads are. We need to know where the read head is for tape 1 and the read head is for tape 2. Okay, this single terminal, this single machine with a single read head. For every step of the computation that this is taking, we want this machine to do some computation which ends up simulating what that single step was over here. Well, the single step over here can move both of its read heads. Okay, but this only has a single read head. So we have to encode that somehow in the tape as well. And the way the book describes this is that you can put a mark on the tape over a character where the read head is positioned on this machine.